All right, so I'm going to review the schedule. Let's see. Now the schedule I'm going to modify just a little bit because I think we were supposed to do this like leisurely hypothesis testing section over like 3 weeks, but that didn't really work out. So the most important thing is chapter 10, which is an introduction to hypothesis testing. I do want to make sure that we cover correlation because that should be part of the introductory course. So let's see how it goes. Chapter 11, where it's hypothesis tests for 2 sample means or proportions. That is not as important as chapter 10, but if I have time, I will put some effort into that, but not over 3 meetings. We'll definitely do that over 1 meeting as opposed to 3. And that's because I want to spend some time on correlation and regression. So I just want to make sure you complete the course based on what I think you should know. As far as tests are concerned, I believe we should probably have a couple more quizzes. So I'll probably make one for next week. And then maybe one for the week after, maybe 2 more quizzes. We still have a 3rd exam, which will cover everything that we've covered since the last exam. I believe we went through chapter 8 in our last exam. So chapter 9, chapter 10, and if we cover something in chapter 11, that'll be in there too. And then linear regression, which is chapter 15, correlation and linear regression. There's also a little section in chapter 2 that we skipped on scatter plots and correlation, which we'll go back to. But definitely we have to cover linear regression in some way. So I will make sure that you get that background too. All right, now, did you both get to watch the video that I posted?
Yes.
Yes, all right. Was it helpful and as an introduction to hypothesis testing? Did you get sort of an idea of what we're going to be doing?
I believe so, yes.
All right, good. So I'm going to do a little bit more of that today. And actually, let me open up that. Let me stop sharing this. I'm going to open up oops. See, I don't think I can minimize this screen here. That's not going to let me do that. Just 1 second. Oh, I know where to go. All right. Once you start recording, you can't minimize the screen for Zoom, so you have to find some other way to open things up. I'm going to open up the PDF that I posted. Here we go. All right. So let's share that again. And I just want to review that and then talk a little bit about some of these topics in a little more depth. And so you understand exactly what we're going to be doing over the next 2 weeks. You can see this PDF, right?
Yes.
Clear? All right. So a hypothesis test is different from a confidence interval because with a confidence interval, we're trying to estimate a population parameter like a population mean or a proportion. A hypothesis test is where we have a pair of hypotheses, one of which is a stated hypothesis about the population parameter. All right. So we're actually going to state something about the population parameter. Now, in the book, if you've going through the book, it does something that's not as traditional as other textbooks do. In the null hypothesis, I state here that we should always use an equal sign. All right. That would include cases where we have less than or equal to or greater than or equal to as possibilities. But I tell people just use the equal sign because that way you don't have to think so much about the null hypothesis. All right. So typically it's the accepted hypothesis. about the parameter that we're talking about, whatever it might be. And the way we write the null hypothesis is with a H for hypothesis, the little zero next to it. And we can either call it H naught means zero, or H sub zero. That's typically how people pronounce that. And two examples of what a null hypothesis looks like is you could have H naught with a colon, and then you have your population parameter for the mean, which is mu. In this case, is equal to 5. I'm just making some number. Or if it's a population proportion, and I think just for consistency, let's just use P for the, not consistency, just for this course, let's just use P as the population parameter for proportion. And we'll use P with a little hat above it for the sample proportion. Because again, most textbooks, that's what they use. This textbook, they're trying to be different. You know, they're trying to be different than others, but typically you'll see P here, and just know the book will use pi instead of P. So P is equal to 0.35. This P is representing the population. The alternative hypothesis would be a competing hypothesis to the null hypothesis. And we're going to use greater than, less than, or not equal to as the symbol or the operations that we're going to be using in the hypothesis. Now the book, again, being different, they like to use H1. I don't know why. Why? Because they say this is H0? I don't know. They use H1. Students who just are learning this, it's better to use HA because they know A means alternative. All right? Most textbooks use A for the alternative hypothesis. It just makes sense, right? Instead of H1. But the book uses H1. Again, very few textbooks use H1. They use HA for the symbol. Again, use a colon, and then you're going to use one. It's going to be one of these three cases. Either we're going to say greater than, less than, or not equal to, depending on the context of the problem. Okay. The same thing if it's a proportion. You use P greater than, less than, or not equal to. The most important thing here is that the number that's used in the null hypothesis has to match the number that's used in the alternative hypothesis. All right. They have to be the same number. All right. Now, as I had mentioned in the video, and Dr. Williams, who was the video in the video, talked about, we're going to assume that the null hypothesis initially is true. Just like in a criminal trial, if you've ever been on a jury, the judge will ask you to assume that the person who is being accused, you're going to consider that person initially to be innocent, unless there's enough evidence beyond a reasonable doubt that the person should be convicted. So the null hypothesis in a criminal trial is that the person is innocent or not guilty, and the alternative hypothesis is that the person is guilty. So the same thing in a statistical test. The null hypothesis, H sub 0, is initially assumed to be true. What we're in essence doing with a hypothesis test is we want to look at the sample data that we have. We want to calculate the point estimate for the population parameter. For example, if the null hypothesis is about a population mean, we want to calculate X bar, the sample mean. If the hypotheses are about a proportion, we want to calculate P hat, the sample proportion. And then we want to determine the following. We want to determine if the sample statistic is sufficiently far away from the population, the proposed population value, that we think it's highly unlikely that that sample statistic came from a population parameter that's stated in the null hypothesis. Okay, it's unlikely. And that way we would reject the null hypothesis to say it's something different. Either it's greater than, less than, or not equal to, again, depending on the problem. How do we come up with this evidence? Well, that's what you're going to start learning today. All right, the procedure for doing this. All right. Now, if we do reject the null hypothesis, that is, we've found enough evidence to reject the null hypothesis and say that the alternative hypothesis is probably true, then we've determined that the alternative hypothesis is statistically significant. All right. There's enough statistical evidence to say that the true population mean is something other than the null hypothesis value. That's one of the reasons, by the way, I like stating the null hypothesis is an equal. Because if you say something like less than or equal to or greater than or equal to, you're going to say, well, which value are we talking about? Are we talking about the number here, or are we talking about something smaller or bigger? So just to make it simpler in terms of determining what value the null hypothesis is stated at, we just state it as equal to. That's why I like it better this way. And that's why I will ask you to write it this way as opposed to the book. All right, which for some students is a little confusing. Now, one of the things is if we do not find enough evidence, then the alternative hypothesis is not statistically significant. All right. It does not mean now what we would say is we do not reject the null hypothesis due to lack of evidence, statistical evidence, but we never say that we will accept the null hypothesis as true. Just like in a criminal trial, if the prosecution, if the district attorney does not find enough evidence to convict, then the jury will say not guilty. But it doesn't mean that person didn't commit the crime. It's still possible the person committed the crime, but there wasn't enough evidence to convict the person. Maybe the police did a bad job. All right. So we never say the null hypothesis is true if we do not find enough evidence to reject it. We just say we do not reject the null hypothesis due to lack of evidence. Now, this chart here is in many statistics books. All right, it's used quite often. Sorry for the little slant here. I guess the paper I was using was at an angle. But now, what is this chart showing? There's two things it's showing. Along the up here, along the columns, I'm talking about reality. Now, the only reason we're doing a statistical test is we're trying to test a proposed reality, proposed value for the null hypothesis. It's proposed because we really don't know. If we knew it, why bother doing statistical testing? So this unknown reality, as far as the null hypothesis is concerned, is either the null hypothesis is true or it's not true, right? There's only two possibilities. It's true or not true. We don't know which one it really is, but we're proposing that the null hypothesis is true up front, all right? Now, along the rows here, we have what's called the result of a test from the sample. In other words, the sample data that we have, we're going to perform a statistical test, and I'll go through the steps of doing that. As a result of the statistical test, you will come to a conclusion. Based on the sample data, you will either reject the null hypothesis because you think there's enough evidence, you know there's enough evidence to reject it. In other words, the alternative hypothesis is significant, or we do not reject the null hypothesis due to a lack of statistical evidence. In other words, the alternative hypothesis is not significant. One of these two will be the determination of the statistical test. Now what we're going to do is match the result of the test to reality, the unknown reality, but we'll call it reality. Along this column is the actual reality that the null hypothesis is true, and along this column is the actual reality the null hypothesis is false. Now, one of these two is correct, but we don't know which one. Suppose we reject the null hypothesis, right? Why do we reject it? We think that the alternative hypothesis is true. There's enough evidence for that. Well, if we reject the null hypothesis, but the null hypothesis is true in reality, we've made a mistake. That's an error. And what we call it is a type 1 error. Now, if we reject the null hypothesis and the null hypothesis is actually false, well, we've made a correct decision. So in this box here, we call it a correct decision. The test is correct. Now, if we do not reject the null hypothesis because of lack of statistical evidence, then if we do not reject the null hypothesis and the null hypothesis is actually true, then we've also made a correct decision. However, if we do not reject the null hypothesis, but the null hypothesis is false, that's a mistake. And that's called a type 2 error, where we do not reject the null and the null is false. So if we consider the examples of a person who is in a criminal trial for, let's say, committing some crime, right? They committed, or they think, the district attorney thinks they committed a crime. If the jury, now, if the null hypothesis is that the person is innocent and the alternative hypothesis is that they are guilty, then if we reject the null hypothesis, all right, we basically, the jury is basically saying, hey, we think there's enough evidence to go beyond a reasonable doubt, and we're going to convict the person. Now, if the person didn't commit the crime, that's a mistake, right? They're going to end up going to prison for something they didn't do. That's called a type 1 error. On the other hand, if there's not enough evidence, if the prosecution doesn't provide enough evidence to convict, the jury will come back and say, not guilty. Right? They're not going to reject the null, that they're innocent. But if they did commit the crime, that's called a type 2 error. So basically, the person committed the crime, and yet they're going to be let go of. All right, they can enter society again. Type 1 error, type 2 errors, that's examples of it. Now, if the prosecutor does their job and the jury rejects the null hypothesis, so in other words, the jury says the person's guilty and the person did commit the crime, then that's a good thing that the person's going to go to jail, right? It's a good thing. So we call that in statistics the power of the test, the power of the test. In this, in the case of the criminal trial would be the power of the district attorney. The district attorney did their job, got the bad person off the street. All right. So in the statistical test, it's the power of the test. Because a researcher typically wants to reject the null hypothesis. That's their goal. That's what they want to do. And if they reject it and they did it correctly, all right. In other words, this box over here, they rejected and they did it correctly. That's called the power of the test. And we want the power of the test. Now, it's a probability. It's a probability that we reject the null hypothesis when it's actually false, right? That's a good thing. So that's the goal, and we want this probability to be high number. Now, the complement of that is the probability of rejecting the null hypothesis. The complement of this would be what? It would be the type 2 error. It would be not rejecting the null hypothesis when the person did commit the crime. All right, that's the complement of it. So beta is the probability of a type 2 error. That's what we call it, beta, the probability of this type 2 error. Therefore, the power of the test being the complement of that is 1 minus beta. And I'll show you in section 7 of this chapter, there's a little something about that. So we'll go over that today, what the power of the test is, so that you would know how to calculate it. Now, the most important probability is what's called the probability of a type 1 error. Why is that? Because, again, the researcher wants to reject the null hypothesis, but there is a chance that they might have made a mistake, right? Now, they hope it's not a mistake, but this type 1 error is something they want to control for. They want this to be low. Because when they do, if they do reject the null hypothesis, they want to be pretty confident that they've rejected it. There's a good chance that the null hypothesis is false. So the type 1 error is called alpha. Alpha. And this is something that a researcher will try to control for upfront before they do their research. So they're going to select an alpha. So what they're basically going to select is some low number, so low probability, like 0.05, like 5%, or 0.01, 1%, or 0.1, 10%, some number that's small like that. And they're going to say something like, okay, I can live with a type 1 error of 0.05, all right, 5%. All right, I can live with that. If if the probability of me being correct is 95%, then I'm okay with that 5% type 1 error. All right. So alpha is 0.05 is something they want something small, and they want to select this. At least they should be selecting this before they do the research. So this alpha, or probability of a type 1 error, is also called the level of significance. The level of significance. Because when they reject the null hypothesis, they're going to be stating that the alternative hypothesis is a significant result. All right. So alpha is the level of significance, and tells the researcher, or basically the researcher is agreed that this is the limit to how much of a type 1 error they're willing to tolerate. Okay. Hope that makes sense. Now, part of the thing that you'll be doing when you do a statistical test is that you're going to be using this alpha. This alpha is going to play a role in determining if your sample result supports the alternative hypothesis or not. Okay, you're going to be using this alpha to make that determination. And there's going to be a couple ways of doing this. I'll show you both ways. And I'm going to actually use that stat key that I talked to you about before, stat key, to do a little simulation with this too, so get you to understand in essence what we're going to be doing. So this alpha is, again, important. And we're going to determine, using this alpha, if the sample statistic, the sample mean or sample proportion, is sufficiently far away from the null hypothesis value of the population mean or population proportion. So to make it highly unlikely that hypothesized mean or hypothesized proportion would have created a sample mean due to just normal variation. That's what we're going to be determining. Is it likely that the population mean? Remember, we're sampling from the population. So the sample means are going to be different from sample to sample. Okay. Some sample means are going to be close to the population mean, some are going to be further away. But the important thing to note is the sample mean going to be so far away from the population, the hypothesized population mean, that we think it's highly unlikely that the true population mean is the one that's stated, and it's something else. All right. So that's what we're going to do. Now, there are 3 types of hypothesis tests. One of them is called a two-tailed test. The other is called a left tail or lower tail test. And the third one's called a right tail or upper tail test. I'm going to show you one method of determining whether a sample statistic supports the null hypothesis or not. Now, how do we determine which test to pick? It's the alternative hypothesis that determines it. And how do we determine the alternative hypothesis? The problem itself, the word problem that you're given will give you enough information to determine the alternative hypothesis along with the null hypothesis. Again, starting on Thursday, I'll show you how that works. But we're going to start doing examples of all of these things, starting on Thursday, going into next Tuesday and next Thursday. All right, basically example after example of doing the hypothesis stuff. But today, I'm just giving you a general understanding of how we do these things. Now, if the alternative hypothesis is not equal to, That means we're going to reject the null hypothesis with either a very small sample mean, in this case it's a mean, or a big mean, one of those two. So how do we do it? Well, we're going to assume a bell-shaped curve. Now, the bell-shaped curve could either be a standard normal, or excuse me, a normal curve, or it could be a T. Remember the T distribution with a mean of 0 and standard deviation bigger than 1. Why do we use the T? Because we don't know the population standard deviation. So we're going to use the sample standard deviation instead. Remember, we talked about that with confidence intervals, and we're going to do the same thing with hypothesis tests. If we don't know the population standard deviation, then we're going to have to use the sample standard deviation in our calculations, and therefore we're going to use T. But for now, let's just look at in general, what the test looks like. So one way of doing this is to take our alpha, the probability of a type 1 error, and if it's a two-tailed test, because it says not equal to here, we're going to divide this in 2. The alpha we're going to divide by 2. So half of the 5% will go to a left tail, half of it will go to the right tail. And we're going to color in the area underneath here to correspond to the 2.5%, 0.025. So that's the area on the left and right tail. Therefore, in the middle here, we have 95%. Now, the way to do this particular type of test is that we're going to say these regions that are colored in, the alpha regions, are called the rejection regions. All right. In other words, you're going to reject the null hypothesis, assuming what? Assuming the null hypothesis is true. Here's the 10, right? We're going to assume it's true, so we're going to actually plot it as 10 in the middle. So our sample statistic will be plotted along this line also. And if it happens to fall in one of these two regions when we plot it, then the decision is to reject the null hypothesis. If the sample statistic falls somewhere in between these two values here in this so-called non-rejection region, we say there's not enough evidence to reject the null hypothesis. So these two areas here are sufficiently away from the population mean so that if we plot the sample means in one of these areas, we say it's sufficiently far away, we're going to reject the null. We're comfortable in doing that, given that the area here is small, right? Which means there's a low probability of attaining that sample statistic, and therefore we're going to reject the null. If it's in this white area here, it means it's not sufficiently far away from the population mean. The sample mean is not sufficiently far away, and we're going to say we do not have enough evidence to reject. So this method I'm showing you here is called the rejection region method. Starting next time, I'm going to show you an alternative method called the p-value method, which is the method that is most used by researchers. Almost all researchers use that method. I very rarely see the rejection region method, probably because it would be harder for somebody who was non-statistically trained to understand what I just said. But I think you guys understand it because, I've been teaching you for a couple months already about, bell-shaped curves and areas under the curve and all of that. Now, the other two methods, this method number 2 is called a left tail test or lower tail test. If the alternative hypothesis has a less than symbol in it, then we're going to take the entire alpha and place it into the left tail. All right, we're not going to split it in 2 because there's no 2 tails in this case. It's a 1-tail test. So 1% in the left tail. The rest of the area here is 99%. We plot the middle to be 0.45. In this case, it's a proportion, population proportion. The null hypothesis gets plotted in the middle. And basically, we check out the sample proportion. If the sample proportion happens to be in this region here, this rejection region, we're going to reject the null hypothesis. If the sample proportion's in the white region here, we're not going to reject the null hypothesis. We'll say there's not enough information. Finally, the right tail test here. If our alternative hypothesis is a greater than symbol, then we look at alpha and we place it entirely into our right tail. In this case, it's 10%. We call that the rejection region. The mean of 100 is placed in the middle. So we have our 10% rejection region, 90% non-rejection region. Again, we plot where the sample mean is. If it's in this rejection region, we reject the null hypothesis. If it's in this region, we do not reject it. Okay? So that's basically the basics of the rejection region method. The book goes through that, but I will be teaching the p-value method since it's basically the easier way to use it. And actually, I'll show you the p-value method using the StatKey software. So let me stop sharing this. Any questions about what I've said so far? Does it make sense to you?
I don't have any questions. It makes sense to me.
All right. How about you, Han? You're good?
Yeah.
Okay. So just give me a second here. I'm going to open up StatKey. I think StatKey would be very useful here as a just give me a second. I'll display it to you in a second. All right, so let me share StatKey with you. We've looked at it before with confidence intervals, but I'm going to show it to you how to. So what we're going to do, I'm just going to do a demonstration. I'm not going to show you all these different things here. I mean, I could. I guess it could be useful, but let's do a test. Let's do a test for a single mean. And actually, what StatKey uses is what's called randomization. All right, it's just a way of doing simulation with the hypothesized mean. So here's a particular case here where we're dealing with body temperature, and we know the mean is 98.6 degrees Fahrenheit. I think this is a good example. And suppose 50 people were sampled from the population, and we took their temperature, and these are the results here. All right, looks like somebody had a fever, 100.8, and we had a couple low fevers, and then most of the people were in the somewhere in 98.6 and below. Some people do run low temperatures. Okay. Anyway, this is 50 people, and the average for the 50 people is 98.26. All right, so that's the average for the sample. Now, the randomization samples are basically samples that are drawn from a population with a mean of 98.6. All right. The method that they use, we don't really need to go into it. This is just a demonstration. So let's choose 1,000 of these samples, or maybe 2,000 of them. All right, we have 2,000 of these samples. All right, they all have different sample means. And again, this is simulation. All right. Now, we know what the sample mean is here. Suppose I click now, suppose I want to check, let's do a two-tail test. Let's do a two-tail test in this case here. We want to see if 98.6 is what is a, we're going to say it's a null hypothesis. And let's say the alternative hypothesis is that it's not 98.6. It's not equal, its mu is not equal to 98.6. So if we're going to, that's a two-tail test. We're actually going to click two-tail to do a two-tail test. Notice it automatically defaults to an alpha equal to 0.05. Now, how do I know it's alpha equal to 0.05? Because it splits the these samples into two tails. We see the red on the left and the red on the right, the dots on the left, dots on the right. All right. And it takes half of the alpha and puts it to the right and half to the left, right? So we know that 0.025 plus 0.025 is 0.05. And therefore, the alpha that's being assumed here is 0.05, but it's a two-tailed test. Now, 98.6 is where? 98.6 is, now notice here that we have these two numbers here, 98.39, 98.816. These are called critical values, right? Critical values, we can call them critical values, right? Where to the left of these, to the left of this number here would be in this 95%, what would we call it? Non-rejection region, right? So the rejection regions are the red dots and the non-rejection regions in the middle here. And 98.6 falls in what? It's in here somewhere, right? It's in this region in here. But that's not what we're looking for. It's not at 98.6, it's 98.26, excuse me. 98.26 is the sample mean. We want to know if the sample mean, where does it exist? Well, 98.26 is down here, isn't it?
Yeah.
It's way down here. 98.26. It's in the rejection region, doesn't it?
Yes.
It's in the rejection region. Now, so we would say, all right, it's in the rejection region, and therefore we would reject the null hypothesis that the mean is 98.6. That's what we do in this case. Now we know 98.6 is what's accepted, right? But based on this sample, based on the simulation, we're going to reject the null hypothesis. Here's an alternative way of doing this. Now, remember the null is in the middle here, 98.6. 98.26 is below the null, correct? So one thing we could do, which would make this a little easier, is I'm going to click this box here, and I'm going to type in 98.26. 98.26. I'm actually going to put the actual statistic, sample mean, right there, because it's below, right? It's right here. This number here is the area to the left of that 98.26, showing 0. This is what's called the p-value. It is the probability, this is how it's defined, it's the probability of getting that sample statistic or something more extreme than that. Now, this is not the p-value, this is 1/2 the p-value, because we have to consider that there's another area corresponding to it on the right. It's the sum of these two. The sum of these two these numbers here, give us the p-value, right? And then what we do is we say, if the p-value is less than or equal to alpha, we reject the null hypothesis. Now remember, alpha is the probability of a type 1 error. It's something that we will accept. We're willing to accept it, right? We're willing to accept that as our type 1 error. So anything less than that, or more extreme than that, less than that means over on this area, or less of an area on this area, on this tail. Any area that's less than that is also acceptable. Doesn't that make sense? If we're going to accept 0.05, a 5% type 1 error, then the sample statistic showing something less than that should also be acceptable. The way I look at the p-value, it's the actual type 1 error based on the sample statistic. Okay. So so this is a two-tailed test. We would simply take the area that we come up with on both ends and add them up, and that would be our p-value, and we would compare it to alpha. If it's less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. Does that make sense? Sort of make sense to you guys?
Yeah.
Yeah, okay. Let's actually do another example. Let's pick another one. New York home prices. All right. So I think I don't know if I showed you this example, 30 homes in the New York area. Right, and I think these are in thousands of dollars. Here's one that's 2.5 million. Here's 1.5 million, like that. All right, and there's 30 of these. Okay. Suppose we want to, and suppose the mean, now suppose the proposed, now you can change the proposed mean here if you want the null hypothesis. All right, we're making it 265,000. Let's make it, I'm going to make it 500 here for the fun of it. All right, so I'm going to make the proposed null hypothesis mean 500,000, and the alternative hypothesis is that it's greater than 500,000. Okay, we're good with that. So we're going to do a right tail test. So I'm going to create some samples, maybe 3,000 in this case here, and I'm going to do a right tail test. Now, suppose I want my alpha to be 0.10. Here alpha is 2.5%. I'm going to make it 0.10. So I'm going to click that, make it 0.10. Okay. Now, what's the mean? The mean is $565,633 for the 30. That's to the left here, right? So it looks like we're not going to reject the null hypothesis.
Right.
Right?
Yes.
Okay. This is my alpha. Remember, 10%. What if I put this number in here? I'm going to actually plot the sample mean. The area to the right, this area here, because it's a right tail test, this area to the right is the p-value. It's 0.262. It's bigger than alpha. Therefore, we don't reject the null hypothesis. So you could see that this p-value way of doing it is just an alternative way of doing the rejection region method, right?
Mm-hmm.
We're just determining with the p-value method, is the p-value less than or equal to the alpha? If it is, we reject the null hypothesis. If it's not, if it's bigger, then we don't. And that's our conclusion. I like this method better because we actually plot the actual sample statistics on here, and then we see what the area of that value or more extreme, right? If it's a right tail test, it would be that value or more or bigger, right? And that area is 26.2%. So that is the error. That's our actual type 1 error. That's too big because our limit of a type 1 error should be 10%. That's what we selected originally. But here it's 26.2%. That's too big. And we say, all right, unacceptable. I can't reject the null hypothesis. I'm going to say there's not enough evidence to reject it. Okay, does that make sense? Now, if we change the test a little bit and we made the null hypothesis 400,000, oops, make it 400,000. And let's make a 1%, a 1% alpha, 0.01. We'll do the right tail test again. All right, so we'll generate a couple thousand or so samples, maybe 4,000. All right, and our null is now 400,000. And we want to do a right tail test. Now we're going to say our alpha is 0.01. And where's our sample statistics? Well, it's well in this area. We don't reject it for sure, right? We don't reject it for sure. And then we want to calculate our p-value. Well, we just replace the 716,667 with our sample number, which is 565.633. And our p-value is 0.096. 0.096 is bigger than our 0.01, 1%, right? Therefore, we do not reject the null hypothesis. But let me make a really interesting observation here. What if the alpha was 10%? What would be our decision?
Not to reject.
Still not to reject?
Wait, no, it'd be to reject.
That's right. Because 10% is our limit of the type 1 error. In this case, it's 9.6%. That's less than that. That's acceptable. We're going to reject the null. So notice that in the same situation here, our decision is based on what alpha is. What alpha is. Now, most fields of study, there's an accepted alpha. Social sciences, typically 0.05. Maybe some of the hardcore science fields might be 0.01 because they want to be more, precise about it. But the important point here is that your choice of alpha, which you should do up front, you shouldn't manipulate this, right? You shouldn't, do your results and then choose your alpha, right? You get a result like this and say, I don't like the 1% alpha anymore because I'm going to make it 10%. That way I could show that my research hypothesis is true. That would be kind of, that's fudging, right? You're fudging the result doing that. You should really pick the alpha up front before you do anything, and then be legitimate about it. Check out to see what your actual p-value is. So the p-values for the one-tail test, so either the right tail test or left tail test, we use the entire value as our p-value. If we were going to do a two-tail test in this case here, if this was an actual two-tail test, just unclick it and do a two-tail test. And let's make the alpha to be, let's just put our number in. Now we have two choices here. We could put it here or here, but since the null is 400 and our sample is bigger than that, we would replace this number with 565.633, right? That's what we do. It makes kind of common sense to do that. Now in this case, it was a two-tail test, and alpha was 0.10, we would not reject the null hypothesis. Why? Because the p-value is these two numbers added together. It would be 0.192 is the p-value. Okay, does that make sense? So in this case, we would not reject the null hypothesis, even if alpha is 0.10. If it's a one-tail test, we would reject it, but if it's two-tail test, we would not reject it. So actually, the choice of which test we have, the alternative hypothesis, plays a role in this too. So you have to remember, two-tail test, you always add the two values together to get your p-value. That's really important to remember that. And we didn't do an example of left tail test. Let's find another data set. All right, pulse rate marriage age, husband, wife. How about heart rate? Let's look at heart rate. 200 people with their heart rates, all right? The mean heart rate, 98.925. Maybe this heart rate for, ICU admissions, all right? So somebody's having some heart issue, racing heart, right? So some people are having 140, 150, 170 for the heart rate. Not great if you're not exercising. All right, so supposed mean is 72. Actually, let's make the mean for somebody who's sick, just for the fun of it. Let's make it 110. That's the proposed mean for somebody who's not feeling well. racing heart. All right. And we're going to do a left tail test in this case here. So we're going to generate some samples. 1,000 samples. We're going to do a left tail test. It always defaults at 0.025, by the way, 2.5% here. And then we look at our 98.925, and we know it's going to be a reject the null hypothesis. We know that's going to be the case, right? So we just put it in here, 98.925. And, 0 is going to be the p-value. It's literally 0, right? Practically 0. This is definitely reject the null, right? It doesn't even matter what alpha is. If alpha is 0.01, we're still going to reject the null. This is actually, this is the this is the eureka of a researcher when they get a p-value close to 0. This p-value is probably 10 to the negative 8 power or something, right? It's really, really small. So this is definitely reject the null, but let's do something even, let's do something that's better than this. Let's make the mu here 100 instead of, we'll do a left tail test again. And again, I'm going to put in my 98.925. Notice my p-value in this case here with the null 100, p-value is large. Typically, alphas are no more than 10%. So this is a case of a strong case. Do not reject the null. All right, the null of 100 is pretty good. All right, it might be wrong, but it's pretty good. All right, so that's a left tail test, where in this case you would say mu is equal to 100, and the alternative would be mu is less than 100. And we're saying not enough evidence to reject the null because the p-value is 0.291. All right, was this helpful to understand the two methods of determining a hypothesis test? You either can use the rejection region method, using the areas, the alpha as your areas, or you can just type in the actual sample statistic and determine the p-value. And then compare the p-value to alpha. If it's bigger than alpha, do not reject. If it's less than or equal to alpha, we do reject.
Mm-hmm.
All right, is that good?
Yeah.
All right, that's really the essence of it. So everything else is just a piece of cake, so to speak. So let's look at the book. Let's go to the textbook. And hold on. Let's pick the textbook. And we'll spend another 15 minutes just going over some basic concepts. And then we'll start the actual testing next time. We'll do 3 sessions. And I think there might be enough time actually to do chapter 11 too. Just to do some examples there. All right. So share the textbook. All right. Again, this is the box we were looking at before. Decision, the decision for the is actually a little bit backwards here, right? They do not reject first and then reject second, but it doesn't matter. It's what I put in the PDFs means the same thing. Now, how do we actually do the testing? I'll show you more about the details later. If we know, oops. All right, hold on 1 second. Let me stop sharing and then fix this. Fortunately, that, nope. There we go. All right, so let's share again. All right. Now, in general, the hypothesis testing involves the following steps. You're going to formulate your null and alternative hypothesis from reading the problem. We'll see how we do that. You're going to select the significance level, which will be given to you in the problem. All right, so that's really not selecting it. You're going to be using it. Number 3, you're going to calculate what's called a test statistic. It's either going to be a Z or a T. The T will only be used when we test a population parameter where there's no information about the population standard deviation. We'll use the T, what's called a T statistic. And that's probably true in 99% of the cases in real research. But if there is a estimated population standard deviation, then we'll use the Z statistic. And then from the Z or the T, we're going to calculate the p-value. That's literally what we're going to do. But there's a, that's the method we're going to use. But in the book here, they do talk about identifying critical values. Now, the critical values would only be used if we were going to use the rejection region method, because the critical values would be based on the alpha. We would use inverse Z, inverse normal, or inverse T to calculate the critical values. Remember, we did something like that with confidence intervals. And then we would create our rejection regions and non-rejection regions. However, as a replacement for that, we could calculate our p-values. All right, we can from the test statistic. Regardless of how we do it, we're going to compare. We're going to use our, if we use the rejection region method, then we'll have we'll plot our test statistic to see if it's in the rejection region or not, or we calculate our p-value and compare it to alpha. Whichever way we do it, we're going to come to a conclusion, and then we're going to make an interpretation based on that conclusion. All right, and I'll show you all of that. There's literally like 6 steps. Now, one of the steps I did not mention is that for any of this to work, now, if we were using simulation through StatKey, what I'm about to tell you wouldn't be necessary. But to do any of these things, to use the Z or T statistics, we have to establish normality of the sampling distribution. And remember, for a population mean, we have to use the central limit theorem, right? Central limit theorem, which says if we don't know the population distribution to be normal, or if we know it to be skewed, then we need at least 30 to be our sample size. If we do know the population distribution to be normal, then it doesn't matter our sample size. That's the central limit theorem. In the case of the population proportion, then we have to do that calculation, n times p, n times 1 minus p, right? If you remember that, and it has to be greater than equal to 5 for both of those calculations for us to use the use the normal curve. All right, so that's part of it also. And if it, we don't meet the criteria, we can't do the hypothesis. By the way, we also have to establish that we've done a random sample too. Random sample is necessary to establish that to run any of these tests. If you didn't do a random sample, these tests don't work. We're not supposed to be. All right, now, in the next section is what we're going to be covering, the next couple sections covering next time. That is, what if we know the population standard deviation? How did we do the test? Or how did we calculate the test statistic? And we're going to use our Z-score formula to calculate the Z statistic. All right, that's the whole idea. All right, we've seen this before when we converted a sample mean to a Z-score. If, on the other hand, if we look at the next section, if we don't know, well, actually, that's not it. Where is it? I think I skipped one here. Yeah, this section here. If we don't know the population standard deviation, then we have to replace it with S, right? And we use the t-score formula. The t-score is same numerator. And notice that in the numerator, what are we subtracting from the sample mean? We're subtracting the hypothesized mean. That number that's in the hypothesis test. And then the denominator becomes what? It becomes the sample of the estimated standard error for the sample mean, which is S divided by the square root of n. All right, well, we'll go through this when we actually do the tests. Then if we did a proportion, then our z-score is going to be p. Now, in the symbols that we're going to be using, it's going to be p hat, the sample mean, minus p, which is the population mean, or p0, divided by the sigma p, which is the sample, the standard error for the proportion. By the way, this is the formula here. Now, if you remember, just a quick reminder, when we did confidence intervals and we used the standard error for proportions, what did we use inside here? Because we didn't know the population proportion, we used the sample proportion inside this square root. But in hypothesis tests, since we have a hypothesized value for the population proportion, we're going to use that, not the sample proportion, inside the square root. So this is something you have to sort of remember to do. Go over that next time. And the final thing I want to go over today, spend a few minutes on this, and then that should do it for today, is what's called the power of the hypothesis test. All right. Now, power of the test is the probability of rejecting the null hypothesis when the null hypothesis is actually false. Now, how do we come up with this idea of a power of a test? How do we calculate it? Well, it would be easier, number one, to calculate what's called the type 2 error, probability of a type 2 error. So let's think about it for a second. I think there's an example here. All right. So suppose the null hypothesis is that mu, let's forget about the less than or equal to. Let's say it's equal to 1030. Has something to do with the number of hours of a light bulb. And the alternative hypothesis, again, HA instead of H1, is that mu is greater than 1030. All right. So this is a right tail test. Now, the alpha, if we were going to do we wanted to calculate where alpha is. All right, alpha is going to be on the right tail. All right, that's where alpha is going to be. Now, what if I wanted to calculate probability of a type 2 error? How would I do that? Well, the type 2 error says it's the probability of not rejecting the null when the null is actually false. But look at the alternative hypothesis. When the null is false, the alternative hypothesis just says that mu is greater than 10,030. What's required for a beta calculation or the power of a test calculation is that we choose a value greater than 1030. We have to choose it. It's not enough to say it's greater than 1030 because we're saying the null hypothesis is false. So what are we going to use for the mean if the null hypothesis is false? Well, we have to pick a mean that's bigger than 1030. All right, you sort of get what I'm saying? For a type 2 error, we're assuming that the null hypothesis is false, and we're saying we're not rejecting the null hypothesis. It's a type 2 error. So if the null hypothesis is false, we have to pick a value that is bigger than 1,030. How do we do that? Well, let's see if they come up with one. Let's assume we pick 1,040 as our mean. All right, we're just picking a value bigger than 1,030. We're going to select 1,040. Now, what we're going to do is, now suppose our sample mean is 1,053.41. That's our sample mean. That's what we came up with. It's a right tail test. But in case, instead of subtracting 1,030, which is the null hypothesis, we're assuming it to be, instead of that, we're assuming it to be 1,040. Right? Suppose the standard error, the sigma divided by the square root of n, is 14.23. That's the value. So we're going to calculate our z statistic, or z, based off of this. All right, and it's going to come out to 0.94. So what does that mean? I don't know if we can see this too well. Can I make this bigger? This is in your book. It's in section 10.7. If you have your book with you.
What page is it?
348.
Thank you.
348. $348. All right, so you both see it?
Yes.
All right. Now, if we make 1,040 the mean, all right, and what if we do not reject, and then we do it's still a right tail test, right? Right tail test. Okay, because it's greater than. We make 1,040 here, and we plot our value, which is 1,053.41. This area here, this p-value, this area here, we're not even going to call it a p-value. This area here is going to be what? This is the power of the test right here. Because we're rejecting the null hypothesis, assuming what? That the value is 1,040, not 1,030. So this probability here, in this region here, is the probability of rejecting the null when the alternative is 1,040. This is beta. This is, excuse me, the power of the test. It's the power of the test for what? The assumed value of 1,040. What if we made we made 1,050 to be, I think this is 1,050. What's 1,050? Doesn't look like 1,060. This should be 1,060 here. There's a little bit of a mistake here. Well, actually, there's no mistake. So 1,040 is here, and here's our sample statistic, and here's the probability of having that sample statistic or greater, given that the null hypothesis is false. This is our power of the test, this number here, which is 0.1736. The probability of not rejecting the null when the null is false, in the case of mu being 1,040, this area here is beta. This is the probability of a type 2 error right in here. This is the probability of type 2 error, and then its complement in this yellow region here is the probability of the power. Now, the probability of type 2 error is pretty large, isn't it? It's large. It's 82.64%. That's not great, because the power of the test is really low, 17.36. So what if we picked what? What if we picked a larger value for mean? Let's pick 1,060. Okay. And here's our test statistic right here. Excuse me, our sample statistic. Notice the area to the right here is much larger, right? 0.6772. This is better. And then the type 1 error is just 1 minus that, which is 0.3228. So this is a better situation. And then finally, if we made our mean to be 1,080, then the probability of rejecting the null when we have 1,080 as the alternative, which is the power of the test, is now 0.9693. This is good. This is strong, right? Strong test. And the probability of the test is only 3%. Okay. The problem is everybody would go with this one, right? The last one. The problem is if we also showed you the curve for the original null hypothesis, which was 1,030, right? And where's 1,030? It's right around here. We drew a curve here. We would find what? We would find that with the smaller type 1 error, you have a larger type 2 error. Okay? That's the problem. The problem is that we can't have a really small beta and a really small alpha. Okay? So we can't always have this situation here. Now, the fact that the power of the test and the beta change based on the value of the mean, the bigger mean in this case here, means that there is a range of values for the power of the test and for beta, a range of values, depending on which alternative hypothesized value we pick. So there's like a family of curves. And if you look on the next page, I think it shows you this. All right. So they show the power of the test along the y-axis and the assumed values from the mean along the x-axis. And notice the curve is shaped like this. Right. Also know that the curve changes based on the sample size too. The sample size, and also based on the sample value too. All of these things. But this curve here is basically what's called a power curve. The power curve is just all the possible values for the power based on what? Based on the particular values of the mean that we end up choosing. Sort of understand what I'm saying? Does it make some sort of sense?
Yeah, I think so.
It says the power of the test becomes stronger as the true population mean exceeds 1,030 by a greater margin. All right, so as you get further away from the original hypothesized mean for the alternative mean, you'll see the power goes up and the probability of type 2 error goes down. But as I mentioned before, the type 1 error actually goes up when the alpha goes up when the beta goes down. So there's a limit to all of this, and that gets into an advanced topic. It's an advanced topic in statistics. But what are you responsible for with this section here? You're responsible for if I give you a specific value in the alternative hypothesis, can you calculate what beta is? Can you calculate what the power of the test is? That's pretty much what I would ask. Okay, and I hope hopefully you'll be able to do that. But that's it. Anything else about that? Is that good?
Good to me.
All right. Now there's more in here. There's a lot of stuff in here about trade-offs between type 1 errors, type 2 errors, the effective sample size on them, and all of that. I'll go over that next time. All right, just spend a couple minutes on that. But really, starting next time, the important thing we're going to be doing is the actual hypothesis tests. All right, and we're going to come to conclusions using either the rejection region method or p-value method, but mostly the p-value method. And we'll just do several examples of all of that so you'll be comfortable with it. All right, and chapter 11 is pretty much like chapter 10, with the difference is that we're going to be comparing two samples or two proportions. All right, so if I just go into chapter 11 quickly, there's a couple different things that I'll go through with you. I'll have to figure out how much of this is really relevant for first semester course in this. Are you guys going to take a second semester in statistics? Is that your plan? Or is this
For now, I'm not sure.
But most likely not. Most likely not. Is that correct?
Well, I mean, okay, almost assuredly not next semester, but it's pretty likely that I'll end up taking another course after this.
All right, because this topic here with two means and two proportions, it's in the syllabus. I can show you some of it. And the issue here has to do with the standard error, because if you're dealing with two samples instead of one sample, in other words, you're comparing men and women or whatever the two populations are. The question is, what standard error are you going to use? And there's a couple different methods. There's one where you pool the variances using a formula like this, but I believe software takes care of this. So maybe we'll use software for this, because this looks pretty complicated, right? I mean, you can do it, no doubt, but there's another method called unequal variances, where the standard error look, I mean, it does look complicated. There's a formula for degrees of freedom and all of that. So I'll look through the Minitab software, see if there's ways of doing this that won't involve a lot of computation. All right, because I think if you took another course now, basically you're going to be comparing the means, subtract, you're going to take the two means and subtract them as your null or null hypothesis. You're probably going to be saying the null hypothesis, the two means are 0, and the alternative hypothesis would be they're not 0 or greater than 0 or less than 0, like that. All right. So we're going to be dealing with independent samples, where the two samples are independent of one another, and there's also a formula for, or a test for comparing two means when the samples are dependent on one another. I'm going to look through Minitab to see if there's a way of doing all this without too much fuss. All right, because again, this if you're not going to take a second course, then it would be good to just review this without getting too much into the formulas. So I will think about that. All right, I'll come up with some solution for next week. But we're going to focus on chapter 10 this week. All right, do some examples of all the different types on Thursday. And we'll continue that on next Tuesday. All right, any questions? Are we good? Any questions about anything I covered? All right.
I'm good.
So again, we'll be doing more of this, doing the actual tests on Thursday. Okay, we'll do more of this. But I think good introduction. Was it a decent one? All right, good. So we'll continue. We'll do the actual practical applications next. All right. So it's late. It's 10 to 10. And if there's nothing else, I'll stop the recording. Any other questions? Han, do you have any questions? No? Okay. My dog is scratching at the door.